Is the microphone on? Sorry.
So I can write some things down. Let me work with a slightly toy example here, where I only keep the S-channel pieces. So I'm going to forget about the subtraction pieces. I'm going to just keep things in the S-channel, so I don't keep writing things down. The story changes in a very interesting way when you have the S, and the T channel becomes richer. But just for the sake of time, let me talk about this. So I'm ignoring the U channel just for this sort of toy amplitude. When I show you results at the end, they'll be for the correct thing. Okay, so now let's just expand in S and T. So if I expand the right-hand side in S and T, let me define GS of 1 plus 2y to be the sum over q, y to the q, GSQ. That's just a definition. So that's going to be for the T part of the expansion. For the S part of the expansion, we know how to do it. Sorry, this is an m squared minus s. Okay, and therefore, I get, on the right-hand side, a sum over this unknown spectrum M and S. As always, the sum is an integral in general. P, M, S. And then I have 1 over m squared from the S expansion. I have some 1 over m squared to the p plus 1, s to the p. And from the T expansion, I have t over m squared to the q, GSQ. Okay, so I have also a sum over p and q. Okay, so from that I can extract the coefficients of s to the p and t to the q in the low energy effective theory. And notice, of course, the overall power of m squared is p plus q plus 1, right? So it makes sense to label these couplings by the overall mass dimension of the operator, which is p plus q, if you like. So I'm going to write this as the sum over this overall dimension d and q, a dq, s to the d minus q, t to the q. And what is this a dq? A dq is the sum over m and spins, this p m s, over m squared to the d plus 1 times g of s and q. Okay? So this is so in the low energy theory, when it has a polynomial expansion, this is the polynomial expansion, and now this is the equation that we're going to be studying. Right, is that clear? We just did a polynomial expansion, and now we want to learn the consequences of two things once again. What are the consequences that p is positive, and the consequences that m squared are positive? Now, before we delve into this particular problem, let's talk about this problem in more generality. Because this is totally ubiquitous everywhere in physics and mathematics, economics, all sorts of places. So I want to phrase the problem generally. Let's say you're in a situation where, after all, we have a whole bunch of numbers here. Imagine putting these numbers into a giant vector, right? And so we're asking the question, what can we say about a big vector that we're interested in that's made up out of some things that were handed, linear combination of some things that were handed with positive coefficients. So we're going to set up that question in generality. Let's say you have a vector A, could stand for amplitude, I is just the vector index. And what can I say about when it's expressible as some P1, V1, plus dot, dot, dot. Let's say we have a finite number of them. We can let the number go to infinity later if we like. Okay? So we're interested in this general problem. What can we say about vectors A that are expressible as a positive linear combination of some fixed set of vectors V? So here, what we know is that the P's are positive, greater than or equal to 0, but I'll just say positive. Okay. And there's a convenient way of thinking about this. The language that I like is that of projective polytopes. So here's how it goes. The first thing we have to decide is when this equation puts any constraints at all on A. I mean, you might naively think if you have a bunch of, two-dimensional vectors, give me 100 two-dimensional vectors, well, I can write any two-dimensional vector it's not putting any constraints at all. I have hundreds of vectors that can express any vector as a linear combination of 100 two-dimensional vectors. And so it's obvious that the V's have to satisfy, an obvious property in order for this to tell you anything about the A's. And the property is that the V's have to all be on the same side of some hyperplane. Okay? So the V's have to look like that. Otherwise, you're not doing anything. Okay? So for instance, this is good. And what does the space of all A's look like in this case? Right? The space of all A's that are a linear combination, positive linear combination of all of these guys is just the inside of this cone. Right? So the space of all A's is somewhere in the interior of that cone. Okay? Just because you can take any positive combination of any of them. On the other hand, if the V's look like this, they're not all on the same side of some line, some plane, and the positive linear combination of these things spans the entire space and tells us nothing about it. Okay? So the first thing that you need to do is see that the V's are all on the same side of some hyperplane. When you do that, it's convenient to write those V's. It's just a basis-dependent statement, but this is equivalent to saying that there's some way of writing the V's. Each VA, I, can be written as some positive CI upstairs, some positive variable here, some AI, and then some BI's downstairs. Okay? Saying they're all on the same side of some hyperplane means that there's some first component of them you can choose in some basis to all be positive. So now let's say that happens. Okay? So now we are putting a constraint on the space of A's. Why is it natural to think of this problem in projective terms? The reason is that it's naturally projective. In other words, it's naturally invariant under rescaling all vectors by positive constants. So let's say I hand you one set of V's and a different set of V's, where the second set has each vector rescaled by a different positive constant relative to the first one. The space of A's is exactly the same in both cases, right? Because I just changed what I mean by the C's. Similarly, let's say you give me an A in the space. Of course, I can multiply it by any positive number, and it's also in the space. So the data that specifies this cone is naturally projective. It's a bunch of vectors modulo positive rescaling. And also the space itself is naturally projective. Okay? Now, let's see how that works here. Because of that, I can always choose some representative of this space where the V's upstairs look like 1, again, times the little V's down here. And now let's see what our formula for A looks like. Our formula for A looks like the sum of P1, Pi, Vi. So the top component would be P1 plus P2 plus Pn. And then here I'd have, and the bottom components would be P1, V1 plus dot dot plus Pn, Vn. That's what the A would look like. And therefore, if I want to use a projective representative of this A, where the top component of A is 1, right? So I can rescale. I can rescale the top component of A to 1. So if I do that, so it looks like 1 little a, then little a is P1 V1 plus dot dot plus Pn Vn over the sum of all the P's. And that, of course, has a very standard interpretation, right? The space of all the A's that can be written in that form as a weighted sum of the vertices is known as the convex hull of the vertices Vi and is a polytope. That's one definition of a polytope. Okay, so if you have, if I draw a two-dimensional example, if I take these vectors V1 through Vn, then if I think of those P's as masses, then the formula for A, the sum of Pi Vi over the sum of Pi, is like center of mass. And when the masses are positive, the A's will just end up somewhere inside this polygon. Okay? But of course, we can have, in 2 dimensions, all polytopes are convex polygons. Beyond 2 dimensions, they can have much more interesting shapes. I don't need to draw tons of them for you, but we can have, these are 2 tetrahedra on top of each other, cubes, truncated tetrahedra. We can have all kinds of more interesting shapes of polytopes in higher dimensions. Okay, but this way of describing a polytope projectively is slightly more convenient for a couple of reasons. In other words, I could just describe it like this and be done with it. But it's more convenient to actually think of it in terms of the one higher dimensional vector, and in fact in terms of the problem as we started off to begin with, that the A is P1 V1 plus dot dot plus Pn Vn. First of all, you don't have to do this annoying divide by the sum of all the Pi's. Okay? And secondly, and it's a general fact of life in geometry, if you're solving any geometry problem ever in anything that looks like in Rn, any problem that does not involve a notion of a distance is much better thought of as a problem in projective geometry in Pn instead of Rn, and is much more conveniently thought of by adding the one extra coordinate, thinking in terms of lines passing through the origin in one higher dimension. And we'll see some reasons for that in a moment. Okay, so, all right, but that's what we're, that's the problem that we're trying to solve then. So when we're trying to figure out when someone hands us a problem of the sort that we talked about, we're really trying to describe the points on the interior of some polytope. And so now here comes the practical problem then. So let's say someone gave us a bunch of 2-dimensional vectors in this, or 3-dimensional vectors, and projectively we have points on the inside of this polygon. Now comes the interesting question. How do you check, if you give me a point, how do you check whether it is or isn't inside this polygon? So let's say you hand me an A. How can I actually practically check? Is A expressible as P1 V1 plus Pn Vn? And you see, precisely because the space of P's is much higher dimensional than this is just a 2-dimensional space. I could have 100 vertices, right? So I can't uniquely solve for the coefficients. Okay? All I want to know is that it can be expressed in this form, but of course there are zillions of ways of expressing the same point, which has minus signs too. Okay, so that's not. So this is a good definition. This convex hull definition is one definition of a polytope. So the one that we just gave, where the vertices are the star of the show. But we need another picture of a polytope, which of course in this case is very simple and familiar. the practical way to check whether a point is inside or not is to see if it's on the same side of all of these edges. Okay? So to do that, we need a different definition. So this convex hull definition is A equals the sum of PV with P is positive. But we need the facet definition, which defines a bunch of hyperplanes associated with the faces, so that has a downstairs index, Wi, Ai greater than or equal to 0. This is a way of cutting out the polytopes with inequalities. So these are two sort of dual definitions of what a polytope is. And what typically happens to us is it's given to us in one definition as a convex hull, but in order to be able to figure out what the shape is, how to practically check whether a point is inside or not, we need to go to the second definition in terms of cutting it out with inequalities. Okay? Now, how can we do this completely systematically? What is the totally systematic way of doing this? Well, let's go back to this example. In this example, so first, a little bit of linear algebra. So let's say we have 3 points, A, B, and C. And I want to distinguish 3 situations. 1 where C is like that. 2 where C goes on the line between A, B, and C somewhere. And C where C goes to the other side. Each one of these are literally 2-dimensional vectors. Each one of these 2-dimensional vectors is projectively represented by a 3-dimensional vector. So I'll call those capital A, capital B, capital C. And now, in the projective space, the only invariant tensor there is the epsilon symbol, nothing else. So the only invariants you ever talk about involve contracting things with the epsilon symbol that I'll always represent in this lecture with brackets. So anytime you see a bracket, those things are being contracted with the only epsilon symbol that makes sense. And so let's see what these various things mean. For example, what does this mean? That C is on a line with AB. This means that if I take the 3-dimensional vectors associated with them, that ABC is equal to 0. Okay, and see if you can convince yourself of that. For example, just very mechanically, you can see that that determinant is A minus B cross A minus C. Okay? And so indeed, that bracket vanishes precisely when the triangle made out of ABC collapses. But it's also for a much simpler conceptual reason, which is that when C is on the line A and B, you can write C as a linear combination of A and B. Okay, so that's what it means for, and if C is a linear combination of A and B, of course, that bracket vanishes. All right, so notions of incidence in projective geometry, of whether points are on lines, planes, etc., more complicated things, are just given by various minors vanishing, determinants made up out of the vectors associated with the points vanishing. Okay, but we can also get a notion of we have to give an orientation to the whole space, but what it means for C to be on one side and C to be on the other side, C is on one side means that ABC is positive, and C on the other side means that ABC is negative. Okay. So let's come back here. So if I think about this problem on the plane, I know that the edges are, I know that these W's I are just the I plus 1s. Okay, are just the vertices Vi plus 1. And therefore, a point A is on the inside of the polygon. Let me just erase this here. We know what these inequalities are that cut it out. The inequalities are just that Vi plus 1, A should be positive for all I. Okay, so this is the facet definition in the case of a polygon. Right. Any questions about this? Is that clear? Sorry? Well, in fact, any convex polygon, no matter how you're handed them, whatever labels you're handed, in 2 dimensions, the shape will be a convex polygon. And this is very, very important. They are ordered then. The convex polygon, they are ordered in the way you see. Okay? I'm going to come back to this point in a moment. This ordering is very important. Okay. Now, let's try to say this a little bit more generally then. So how can we decide what the shape of a polytope is in general, what its facets are in general? Well, if there's a face, then there's some collection. So if I have a bunch of vectors vi, now I runs from 1 to n plus 1 in general. I want to see if a particular collection, V, let me call them A1 through VAN, is a particular collection, could this collection be a face? Could they lie in a face? What it means for them to lie in a face is that all the other vertices of the polytope either are also on that face. So you don't have to have, for example, in 3 dimensions, it doesn't happen in 2 dimensions, but in 3 dimensions I can have something like a square pyramid, right? If I have a tetrahedron, all the faces are triangles and they just have 3 vertices. So you have to have at least n vertices on a face. But you could have more than n vertices on a face. In this case, for the square downstairs, I have 4 vertices on a face. Okay, but if you have a face, there has to be at least n vertices on it. And it being a face simply means that all the other vertices are on the same side of it. Right? So in this case, well, only this one is on the same side of any 3 of these guys, and so on. So what that means is that you must be able to find n v's. If it's a face, then it must be the case that if you look at this VA1, VAN, this determinant, and then VB, for all other B, that this is either equal to 0 or positive for all other B. And therefore you see that the shape of the polytope is entirely captured by the following data. If you give me a bunch of V's, the shape of the polytope, what its facets are, everything about it is rather redundantly, in fact, very redundantly, but is captured by the following information. So if you're given a collection of vectors, so given a collection of VA, I have to look at the following list, all the determinants that I can make with any n plus 1 of them. And I have to take, I don't care about their actual values, I just care whether they're positive, 0, or negative. That's all the information. Okay? This has a fancy name, it's called an oriented matroid. Oriented means you care about the sign. Anyway, we won't need to use the name for anything, of course, but it tells you something, that whenever you're handed a problem like this, you have a bunch of vectors, you want to find all vectors that can be expressed as a positive combination of them, the absolute first thing you should do is compute all the determinants, okay, because that's what has the information, right? That's the dumb, straightforward thing to do. Okay? Now, you see, this problem is also, I mean, it's systematic, but it can be infinitely hard if you have, for example, infinitely many vertices. Okay? So in general, if you're handed the vertices of a polytope, we don't know what the facets are. I mean, we know systematically how to do it. It can be practically very hard to implement this literal dumb, straightforward procedure. And other things, linear programming, other things are very effective for finding out what the facets are. Okay. But of course, when mathematicians have been studying polytopes for over 100 years, what it means to study polytopes is to come up with some class of them where you understand everything about them. You understand the vertices and the facets and all the structure, right? That's not guaranteed to be possible for the reason I hope I made clear. So there has to be something special about the oriented matroid in order to be able to say something about, in order to be able to say something ahead of time about what the structure of the vertices, facets of all dimensionality are. Okay? And of course, there are zillions of different, not zillions, but lots of different kinds of interesting polytopes that can be understood in this way. But there's one class of polytopes that I want to now talk about, which are going to make an important appearance in our effective field theory story and have previously made a very important appearance in the story of the amplituhedron and scattering amplitudes and positive Riemannian and all of that stuff. And these are, their name is, they're called cyclic polytopes. And these are polytopes for which there's a natural ordering on the vertices. So you give me a bunch of vertices, v1 through vn, in any number of dimensions, but they're naturally ordered. Okay? And as we saw, this is sort of true, trivially, for all polygons. But if I draw you a cube, there's no obvious ordering for the points on a cube. Okay? So you might not think that there is any interesting notion of ordering associated with shapes in higher dimensions, but there is, and that's what the cyclic polytopes are about. So you can think of them as the most straightforward generalization of the inside of a polygon. Now let me actually go back to the polygon example and see what we actually know about the polygon. So what is the oriented matroid for a polygon? Okay, I told you all the information is contained in the oriented matroid. What is the oriented matroid for a polygon? Well, it's obvious what it is here. For a polygon, all these minors, all these determinants, VA1, VA2, VA3, they're all positive, so long as the A's are ordered. Okay, so that's just saying that every triangle in this picture has the same orientation. Okay, and so therefore, VA1, VA2, VA3 is positive for all the ordered A's. Okay? So cyclic polytopes are just a direct generalization of that. You take that as the inspiration, and you say that the oriented matroid, cyclic polytope, is the convex hull of a collection of vectors that satisfy the important property that VA1 through VA n plus 1 in general here are all positive when the A's are ordered. Okay, so again, these are just words, but if I stack the vectors, if the vectors are k-dimensional, and I stack them into a k by n matrix to represent all the data, then I have a k by n matrix, and what I'm saying is that all the ordered minors of that k by n matrix are positive. Okay? If you thought of that k by n matrix instead of a stack of vectors, if you thought of it instead as a stack of k row vectors, their span specifies a k-plane in n dimensions, and then the word is that plane in n dimensions is in the positive Riemannian. Okay, so all these are just the same word. But the basic idea, the basic fact is that you have data, you have a matrix with all of its minors positive. Now, what's special about this? Yes?
Sorry. When you mean a cyclic polytope, you mean that all minors or order minors have to be positive when contracted with the epsilon symbol? Or
Yes.
do you mean, okay.
All of them are positive. All of them are positive. Not just all of them are positive. But the reason why the ordering is important is that minors are antisymmetric. Determinants are antisymmetric. So for the sign to be meaningful, I have to tell you how they're ordered. And that's why there has to be this ordering on them. Okay? Okay, now, just as in the case of the polygon, when this is true, we can actually predict ahead of time what all the faces. We can also give a definition of the cyclic polytope in terms of faces. So let me tell you, and so that's the entire point, is that you can say everything about its facet structures. Let me tell you what the faces are. And they sort of generalize what we know about the faces for the polygon. In order to do it, let me quickly, without looking at a picture, let me prove to you, go back to the polygon and explain why the edges are all of form I plus 1. So back to the polygon, which is the two-dimensional cyclic polytope. I want to see, is some VAB, is it an edge or not? Is it a face or not? Well, to do that, I have to see whether C, for all other C's, whether this is equal to 0 or bigger than 0 for all C not equal to AB. Right? If it is, then A and B are, if it is, then VAVB could be a face, could be an edge. Well, so let's see, is this possible or not? It has a chance because we know that when the minors are ordered, they're all positive. So it's a chance for there to be something positive. But let's see what it looks like. So say I have A here and B here. This is an index space. So this is 1, 2, 3, A, B. Okay, if I have it like this, then if C is out here, no problem. That minor is positive. If C is back here, also no problem. The minor is positive. Why? It's out of order, but I can push it through two things to put it back in order, and so it's positive again. But if there's a gap between A and B, I'm dead. Because when C is in the middle there, it will have the opposite sign. Okay? So that's how I see if VAVB is going to be an edge, there cannot be a gap between A and B. They have to be stacked right on top of each other. So that's how I conclude that the edges of the polygon are II plus 1. Okay? Now let's immediately generalize that to any even dimensional cyclic polytope. So let's say we jump to 4 dimensions. Now we can't visualize it anymore, but if I want the 4-dimensional cyclic polytope, now I want to ask whether a VA, VB, VC, VD has a chance to be a facet. This would be a tetrahedron, 4 points that lie on a tetrahedron that lie in a facet. So then it would have to be that the 5th point, VE, that this is positive for all E, or all the same sign for all E. Let's see, is that possible? Go back to exactly the same picture. Once again, I have A, B, C, D strewn around. And now, what's going to happen? Again, I'm screwed. If there's any space between A and B, I'm screwed. If there's any space between C and D, I'm screwed. Right? So we learn that the only way it can happen is if A, B, C, D look like I plus 1, J plus 1. See, if it looks like I plus 1, J plus 1, then wherever everyone else is, you have to only hop over an even number of indices to put it in correct position. Okay? See, that's pretty cool. You can't visualize it, but the facet structure of these cyclic polytopes for even dimensions is the generalization of the II plus 1 for the polygon, but it's II plus 1, JJ plus 1, KK plus 1, LL plus 1, and so on. Okay? So that's what it is for the even dimensional cyclic polytopes. And I'll leave it as an exercise for you to play with the odd dimensional ones. So there's a little interesting even-odd difference. For odd dimensions, the facets look like they're, for example, for the 3-dimensional cyclic polytope, it's V1. V1 and Vn are special. So for the three-dimensional cyclic polytope, it's V1 VI VI plus 1 and VI VI plus 1 Vn. So you have those two. For the five-dimensional cyclic polytope, it's V1 II plus 1 JJ plus 1 and also II plus 1 JJ plus 1 Vn. Okay, so that's a little exercise for you to play with. But the important point is that we know everything about the facet structure ahead of time. So if someone hands you a collection of vectors, you look to see whether all the minors are positive, then you know everything about what the convex hull of those vectors looks like ahead of time. Okay? And you can determine what the facet structure looks like ahead of time, just because of this little small combinatorial argument. Okay? Yes?
Sorry, because I really cannot visualize that. Is there a way to understand this by something related to permutation groups or somehow?
No, there's no better way of understanding than what I just told you, as far as I know. Okay? I'm sorry. There are probably worse ways of explaining it, but there are no better ones. We can talk about worse ways later, though, then. Okay. Now, let me just give you, so it's not so abstract, let's give an example of a collection of vectors. Give an example of a collection of vectors that are guaranteed to have all their minors positive. So here's a beautiful classic curve. Mathematicians, physicists, everyone loves. It's an n plus, it's n plus 1 it's an n plus 1 dimensional vector, point in Pn, and is parametrized by a real parameter t, and it's called the moment curve. And this is now a very simple example that if you compute this minor Vt1 through Vtn, Vtn plus 1, so you just choose any n plus 1 points on this moment curve. And if you compute this minor, this is just the determinant of 1, T1, blah, blah, T1 to the n, 1, Tn plus 1, Tn plus 1 to the n. And this determinant has the obvious property that it vanishes when any two of the t's are equal to each other. Therefore, it has to have a root when any two t's are equal. And then just by degrees, you're done. There's nothing else that it can have because it has the right, this polynomial already has the right degree. And so we've computed the determinant. This is the famous Vandermonde determinant you've seen all over the place in physics. Okay? So, very nice. Now, and so it's clear that if the t's are ordered, this determinant is positive. Okay? So we needed an ordering, that's fine. So you take a moment curve, you take any n plus 1 points ordered on a moment curve, the convex hull of those points is a cyclic polytope. In fact, that's, if you Wikipedia search cyclic polytope, that's in fact how they'll define it, as the convex hull of points on a moment curve. They don't have to be on a moment curve. All that matters is that all the minors are positive. Okay, so that's the... Now, there is another beautiful feature that I don't have time to... It's here we just did a computation. There's a more conceptual reason why these determinants are positive. And so I don't have time to explain... I don't have time to give some of these more conceptual explanations. But let me tell you something that you can verify yourself just to see that it's not... that there are already very simple cases where simply computing the determinants is clearly not the way to go to understand something. There's more going on. Okay? So for instance, if these t's are also positive, so not just that they're ordered, they're all ordered, but they're also bigger than 0, then much more is true about this matrix. Not only is it true that this giant determinant is positive, but if you take any submatrix, any subminor of this matrix is also positive. You take any rows and columns of this matrix, and the determinant is also positive. So another way of saying it is, you don't have to have it be 1, t squared, t cubed, t. It can be 1, t cubed, t to the 7th, t to the 8.5. You know, it can be any ordering to the exponents will also suffice. Okay? And then in that case, flat out computing the determinant is not a very effective way of proving that it's positive, but there's relatively quite simple conceptual reasons why that's true. I'm mentioning that only because it'll be relevant for the 15 minutes that I have to talk about the connection to physics. But okay, so any questions about this? So now we have talked about if you're ever handed a problem where you're looking at the positive sum of a bunch of vectors, first you should decide whether it tells you anything if they're on the same side of a hyperplane or not. That's very easy to do, for example, by noticing some components of these vectors are all positive. Okay? You typically don't even have to change a basis to see it. I mean, the way it's handed to you makes it obvious that that's fine. But then in order to figure out what the shape is, formally it's in the oriented matroid. So the first thing you should do is compute some determinants and see if there's any pattern in the signs of these determinants. If the data is ordered in some natural way, you should be thinking about cyclicity, because cyclic polytopes show up all over the place. They have many extremal properties. I'll just mention one of them. Cyclic polytopes are special in the world of all possible polytopes as being the objects that maximize the number of facets. So if you give me a polytope with, any fixed number of vertices in any number of dimensions, and then ask for other polytopes, any polytopes that maximize the allowed number of facets of all dimensionality compatible with the total number of vertices, then cyclic polytopes are the objects that do it. That's one of a variety of interesting things about them. So if your data is ordered, then you should be looking out for whether all these determinants are positive, in which case you know that the convex hull looks like a cyclic polytope. All right, so now, let me go back to our physics problem. And remember that what we had was ADQ is the sum of PMS over m squared to the d plus 1 GSQ. Sum over m and s. And let's see how this has the character of the problems that we just talked about. So to begin with, let me focus on the case, let's say q equals 0. So in other words, we're only interested in powers of s. And then we have something very simple. I'll call it just A0, A1, A2. I won't put the comma. Sorry, this is, so Q is 0 here. So this just looks like the sum, PM, sum over M. And notice that I can just, since I'm putting Q equals 0, GS is just some number, okay? GS at Q equals 0 is just the value of the Gegenbauer polynomial in the forward limit, so it's positive. I can just absorb that into what I meant by P. So this is some positive number P hat over M squared. And then here I have 1 over M squared, 1 over M to the 4th, etc. So if I'm just looking at the coefficients in the powers of S, then already I learned something interesting. So let me just redefine, define x to be 1 over m squared. Then I see that A0, A1, blah, 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 A2 can be written as a sum over x, px that I don't know but is positive, times 1x, x squared, etc. Okay, so in other words, I don't know what the spectrum is a priori, so I don't know what the values of x's are. I don't know what the p's are, of course. They're positive. So all I know, however, is that this vector of a's is in the convex hull of the full continuous moment curve. Right? So, of course, we learned that all the A's are positive. That's trivial. Okay? And that fact they're all positive was what I started in the first lecture, is that the fact that all the coefficients of s squared, s to the fourth, all of them are positive. Here I threw out the U channel just for my toy model here. If I put it back, I would only be able to make the statement for the even coefficients. Okay, but let me just stick with this toy model for now. So in order to see that there is some, in order to see what the nature of the constraint is, let's look at the first non-trivial case. Where I just keep I keep the first three coefficients. So this is in the convex hull of 1x x squared. So if I draw a two-dimensional picture then, in the space, let's say the ratio of everything to A0, A2 over A0, A1 over A0, the moment curve is just this parabola. Okay? And I have to have that x is positive, so it's this part of the parabola. And so saying that I'm in the convex hull of the moment curve means if I just plunk down any points here, it's anything I can get in the center of mass there, which is clearly, just pictorially, anything in that picture. So this is what I learned already in this two-dimensional case, is not just that these things have to be positive, but they have to lie inside this parabola. So that tells me that A1, I can say A0 is positive, A1 is positive, but also that A2 over A0 is bigger than A1 over A0 squared, which is the same as that this A2 A0 minus A1 squared is positive. And all of those are actually subsumed as a simple statement about a little matrix. So if I take this set of numbers A0, A1, A2, I can associate this little two-dimensional matrix with it. And the statement that this is in the convex hull of the moment curve, which is just the parabola here, is equivalent to the statement that all the minors of this matrix are positive. A0 is positive, A1 is positive, A2 is positive, but also A0, A2 minus A1 squared is positive. Okay, and that ends up being the general statement. This is a statement that was known and rediscovered in various contexts by mathematicians in the 1930s, and then again in the 60s, and then again in the 80s in various different contexts. The earliest context is the theory of Stieltjes transforms, which is very much related to what we're doing here. But anyway, the claim is that the constraint on these A's is exactly that A0, A1, A2, okay, you naively have this vector of coefficients, but you associate with it a matrix called the Henkel matrix, which is A0, A1, A1, A2, A2, A3, and etc. The defining properties of the ij element of this matrix is the I plus jth element of the vector. And the claim is that A is in the convex hull of the moment curve if and only if this capital A is totally positive. And the word totally positive in this context means that all the minors are positive. Okay? So you see, the trivial statements that they're all positive is about the 1 by 1 minors, but it's extended to a statement about the general n by n minors. Okay? So these are the constraints one class of constraints I promised you at the beginning. There is an infinite number of nonlinear constraints that relate the different higher dimension operators to each other. This is what makes it impossible to have dimension 6 operators suppressed by a TeV and dimension 8 operators, dimension 10 operators suppressed by a million TeV. Okay? And so you see that this total positivity of the coefficients is encoding the positivity and propagator structure just in the forward limit. 1 over s minus, so there is some dumb positivity associated with 1 over s minus m squared. The fact that you have a positive thing over s minus m squared turns into a statement about total positivity for the coefficients in the sense of all minors being positive of the expansion in the low energy effective theory. All right, so this is one kind of positivity. And can I have maybe 5 minutes? So I want to say something about the other one, then I'll show some plots. And then. Now let's look at a different direction. So I'm going back to my formula. ADQ is the sum And now let me do something else. I now just want, before I put Q to 0, now what I want to do is just study the ADs for different Q at a fixed value of D. So in other words, now I'm studying all the higher dimension operators like S, S to the fourth, S cubed T, S squared T squared, and so on. All the ones with the same units, with the same total power of S. All of those things have the same units. So whatever constraints we're going to get on them will be linear. They're not going to be these funny non-linear constraints. Okay? By the way, I didn't prove that last statement to you about the total positivity of the Hankel matrix. I encourage you to play with it. As you'll see, it's closely related to what I told you about the moment curve itself. That if you take the determinant, if you take the moment curve, when t is positive, it's totally positive. All the little minors are a positive. So that fact is closely related to the Hankel statement. Okay, well, let's go back to this one. Now I'm working at fixed D. Because I'm working at fixed D, when I'm doing the sum over M and S, well, D is the same for everyone. So for fixed S, if I sum over all the M's, I'm just going to get some positive number that depends on S. Right? So if I'm working at fixed D, D fixed, this is some sum of some curly P that just depends on S, G of S, and Q, where P's are positive. So now I have a different problem. I have more of a classic polytope problem. The previous problem of the moment curve was also a polytope problem, but because the points could be continuous, in the end we had to ask this continuous question about the convex hull of this continuous curve. This is much more classic discrete problem now. I've fixed D, and so I think of this as the vector Q being the vector index. So if I look at AD comma 0, AD1, blah blah, up to AD D, I guess. Yeah, ADD plus 1. Whatever it is at the end, I'm sorry. Okay, this is the sum of PS of now GS0, GS1, etc. Okay, so if I stop at a fixed dimensionality, what I get is the convex hull of a bunch of vectors that are now labeled by a discrete index. Okay, just spin. But what I'm doing is taking the first. I'm just taking if I want to have a three-dimensional vector, I take the first three coefficients in the Taylor expansion of the Gegenbauer polynomials. Okay? And it's the convex hull of all of them. Except there's infinitely many of them. Okay? So now we have to do a different computation. To understand this geometry, we have to look at the determinants now made up out of the Gegenbauer polynomials, of the Taylor coefficients of the Gegenbauer polynomials. And these also turn out to be positive. Okay, so these are also give us a cyclic polytope. Okay, so this is the thing that I showed you last time. For the sake of time, let me just not write it again. Okay, so but let me say what the claim is that if you take this matrix, this is the matrix of Gegenbauer. So this is spin equals 0, spin equals 1. So here the ordering is, there is a natural ordering. The ordering is in spin. And now I take the coefficient of y to the 0, y to the 1, and so on. And I get this matrix 1, 0, 0, 1, 1, 0, 1, 3, 3 halves, 0, etc. If I'm doing it for Lejeune. But for any dimensions, all the minors of the Gegenbauer matrices, GS1 up to GSD, are positive when the spins are ordered. I must say that even in this case, we don't have a conceptual proof for why this is true. we do have a proof for why it's true simply by computing the determinant. Okay, so using the generating function and playing with a few tricks, you can actually compute the determinant, analytically compute it, and see that it's positive. I won't write down the formula for you. It's a quite nice formula, actually, but just for the sake of time, I won't write down the formula. But when I say we don't have a... Yeah. What's going on? Oh, okay, good. Actually, I don't think... I don't have that formula here, but I want to show some plots anyway. All right. Thanks. Let me come to this in a moment. Okay? Don't pay attention to that yet. So when I say that there's no conceptual proof, I mean that, a proof that doesn't involve just flat-out computation. This fact was known for the case of two-dimensional Gegenbauer polynomials when they're just cosines. Okay, Gegenbauer polynomials are Chebyshev polynomials in the case of 2 dimensions. They're just cosines. And Chebyshev knew that all these minors are positive. In fact, there are sort of essentially 2 earlier appearances in the last few hundred years of 150 years or so of this phenomenon of total positivity. And the first one was Chebyshev noticing this fact about the Chebyshev polynomials for reasons to do with interpolation theory. But it's true for general Gegenbauers in general number of dimensions. So Chebyshev had a conceptual proof for Chebyshev polynomials. For the case of cosines, it's a very, very beautiful proof, but that does not extend to the general case. So we still don't have, I think, a really good understanding for why it's true, but it is a true statement. I should say that there's a related statement. This thing about the Taylor expansion seems a little bit funny, but there's a related statement that if you actually just simply evaluate, so here we have x equals cosine theta. So here's the physical region between -1 and 1. Normally we care about the physical region here, but out here is the Lorentzian region for the rotations, where x equals cosh eta. And it is, and out here, this positivity statement is equivalent to another one, that if you simply evaluate the Gegenbauers at a bunch of ordered points, but for x bigger than 1, then the matrix, which is just G of Si evaluated at location xj, that determinant is positive, again, when all the spins are ordered and all the x's are ordered. Right, so it's somehow a more naturally Lorentzian statement. It's not it's a statement about the Lorentzian rotation group, not the Euclidean one. And while I've tried many different ways of trying to interpret this statement in some standard quantum mechanical way as a norm of some state or something like that, it does not want to be thought of that way, as far as I can tell. And one indication of that is that the object is not actually strictly positive. It's only positive in some ordering. Okay, so that ordering has to make an important appearance in whatever your understanding is. It doesn't come out brutally as a sum of squares. It's not a sum of squares. It's something that's only positive in a certain ordering. So that's one indication that it's something rather different. This is another one that it's a more naturally Lorentzian statement about positivity. Okay, but what does this tell us? This tells us that the coefficients of now in a given column, that all those coefficients are also inside the convex hull of the Gegenbauer polytope, the cyclic polytope whose vertices are given by the Gegenbauer polynomials. And so it isn't just that, so all of these higher dimension operators for the given units have to lie inside very specific shapes. And those shapes are given by God and Gegenbauer in terms of these, okay. Now, so now let me show you what some of these things actually look like, and so that's what we'll finish up with. Everything I told you here was for these toy examples, where I ignored the S channel. When I ignore the U channel, when I have both the S and the U channels, I'll just say it in words. What you have to do, you can see that there are going to be some minus signs from the expansion of the U poles. Okay, so what happens is that half of the operators you can't say anything about. Roughly speaking, you're taking these cyclic polytopes, for example, and half-dimensionally projecting them down to the ones where the power of S that makes an appearance is even. If you like, because you have SU symmetry, you're really working in terms of the variable S minus U, and you have to work with things that have even powers of that variable S minus U. The other ones you can't say anything about, okay? There's a half-dimensional projection, and so you have what used to be a cyclic polytope, but you're projecting it through half of the directions down to a new polytope. The new polytope is not exactly cyclic anymore, but it's asymptotically cyclic. So, you know, when the vertices, when the spins get large enough, then some order 1 number, they go back to looking exactly cyclic, but down in the bottom, they look a little different and more interesting. And we can try to understand them. We don't know how to, we don't have an analytic understanding of them for all spins. Sorry, for all dimensions, but we can understand them one set of dimensions at a time. Anyway, and furthermore, when you're dealing with when you also have to talk about spin, the helicities of the external particles. So we also have we have to work with the spinning Gegenbauer polytopes, the spinning Gegenbauer polynomials. But anyway, all those things are technicalities, and you can do all of them. So here's what the final answer ends up looking like. So I'm just going to show you some pictures for photon and graviton scattering. Okay, so for instance, for pure photon scattering, after you take out the helicity information, we're now talking about the coefficients of powers of z and t, where z is this variable s minus u. And everything out in front is taking account into helicity information. So the nonlinear constraints are exactly the same as the one that I was telling you in given rows. So here I'm just telling you about these new ones that, about the ones involving the Gegenbauers, the ones that are giving you relations between coefficients of the same dimensionality. So, for instance, in the simplest case, I'm talking about the coefficients of z squared and t squared. So this is a one-dimensional space projectively. And so all of this business about the Gegenbauer polytope tells you that the ratio of those coefficients is bigger than the number -7/20. Okay? Oh, do you have a... Okay. So that number -7/20 comes out of... oops. What am I doing here? This one doesn't seem to work. Is there another one? Oh, this one. Whoops. No? This one also doesn't work. What am I doing wrong? Okay. Okay. Well, I can point here on the screen, actually. So, all right. So anyway, so you see that number. Okay. Oh, it just works. Okay, great. Thank you. All right. Now, the next case we're talking about the coefficients of z to the 4th, z squared, t squared, and t to the 4th. And now you have to decide how you plot this two-dimensional space, but there's a particular way that we like to plot it. Anyway, in this two-dimensional space, you have to lie inside this particular polygon. You see, it's a quite narrow region that these ratios of coefficients have to lie in. And so you see, the vertices are indeed, they're labeled by the spins of the particles. And now you see something a little funny here. You start at spin 4, and then 3, and then 5, 6, 7, 8. That if it was dead cyclic, it would have been 3, 4, 5, 6, 7, 8, but that's an effect of what I told you. When you project these cyclic polytopes half-dimensionally down, there's a little bit of funny stuff at the bottom, and then it looks cyclic at the top. So in this case, it's the reordering between 4 and 3 at the bottom. You'll notice that, of course, there's no spin 1 here because of Yang's theorem. Okay, so spin 1 particles can't couple to 2 massless particles. The spin 2 could have been there. Where is it? You also don't see 2. 2 ends up actually going inside the convex hull under this half-dimensional projection. So that's also part of this little funny business at the bottom. But anyway, asymptotically, it's cyclic like this, and we go all the way up to infinite spin, but you live inside. Yeah. Yes. Yes. No. I mean, the actual amplitude is not STU symmetric. You do in supersymmetric theories, but not here. Yeah, not in general. These are badly drawn pictures. We'll have much nicer ones in our paper. This is just from an old talk. But this is what the three-dimensional polytope looks like. Now in the case of e to the 6, e to the 4, t to the, all these guys, the three-dimensional region, you have to lie inside this three-dimensional region. You see, it's very skinny. It's a relatively skinny region. That's kind of surprising that these regions are as skinny as they are. Now what does it look like for gravity? The graviton-graviton scattering, our graviton-graviton scattering in the real world. For the coefficients of the analog, you strip the helicities off. The analog of z squared t squared is bounded by negative 11/36. Very similar looking picture in 2 dimensions. I won't show you the picture in 3 dimensions and so on. But just so you see what some of these numbers look like. Again, there's some amusing things at the bottom. There's a reordering 6, 5, 7, 8, and spin 4 is absent. Spin 4 ends up inside the convex hull. Okay. Spin 3 and beneath are forbidden by Yanks there. All right, so those are some examples of what these constraints look like. I should say that I don't think I have that here, unfortunately. Do I? No, I don't. Well, I believe that too. But if you plot in these pictures where you actually end up from known UV completions, string theory at tree level, field theory at 1 loop, and so on, you find that you're close to the boundaries of these allowed spaces. Okay? But you're actually close to the boundaries down near low spin. And furthermore, different theories end up surprisingly close to each other, close to this boundary. So whether it's a field theoretic UV completion or string theory, different string theories, they all sort of pile up pretty close to on top of each other, at least in the low dimensional versions of these plots that we've made. Somehow, healthy theories are not taking advantage, as far as we can tell, of maybe there are more fine-tuned theories out there that do, but don't seem to be taking advantage of all the space that is available. And one mechanical reason is that the effect of higher and higher spins is typically damped in these residues in reasonable theories. For example, I forgot to show this earlier. I'm really finishing up, but I forgot to show this earlier. Just if we go back to that box integral, everything that I told you about the dispersive representation of box integrals, that we can do things at small t and so on. And this is a nice exercise. Everyone wants to copy down this formula and go try to derive it. This is what you get from doing the loop integral, but this is the Gegenbauer, the dispersive representation of it. Okay, so in this case, you can indeed write it, the whole integral as an integral over the cut, and this is the discontinuity across the cut, where you can compute what these coefficients are. You can compute what the coefficient of the spin s guys are, and I've just written down the answer, even how to set up the computation. It's a nice calculation to do. So you can extract these coefficients, and of course you find that, so this is what an experimentalist producing a particle at loop level may well conclude, that they're producing a tower of higher and higher spin particles with the amplitude for the cross-section for producing the higher and higher spin ones going down. Okay, so if you plot those functions fs, they indeed fall as you go to higher and higher spin. Also, we know in string theory, of course, this is also true. When you sit there whereas in all of the constraints that I was talking about, we're not seeing any of that. We don't care anything other than the coefficients of these Gegenbauers are positive, right? The coefficients of these things are positive. And that's because there's a bit of physics we have not put in here. And the physics that we have not put in, all we've done is the most primitive possible physics of causality and unitarity. That's it. We have not really asked if these amplitudes are UV complete in any meaningful way. For example, we have not imposed the constraint that at large energy fixed angle, so big S and T with S over T fixed, that the amplitude should not increase, or even sort of primitive things like that. We have not put it. So it's very likely that if we put those things in, there are more constraints on the structure of the low energy effective theory. We've just put in very primitive things about causality and unitarity, and that might explain why we don't probe the entire region of space available here. Nonetheless, there are these infinitely many nonlinear constraints on the structure of the low energy effective theory. And let me just say one final thing. So everything here has been about the higher dimensional operator. I've said many times that we're ignoring we're ignoring the effect of the running of these operators at low energies. So strictly, you can, for example, imagine measuring them at low energies and running back up to any scale you want to apply these constraints. But it's clear that exactly the same positivity statements continue to tell you something interesting about the discontinuity across the branch cuts, even when you go to low energies. And so you should be able to make interesting statements about signs of beta functions and other things like that for the higher dimension operators too. Now, this is something that even before getting to fancier things with the infinitely many operators, infinitely many constraints, we can already talk about in a very simple setting. Let's go back to talking about extremal black holes quickly. So there, when you have an extremal black hole, in the action, R and F squared are comparable to each other. And therefore, if you're talking about higher dimension operators, the operators that can affect the mass to charge ratio of extremal black holes to leading order, which are comparable, are F to the fourth, F squared R, and R squared. Okay, those are the three things that are comparable. And therefore, you need to have some correct sign. Combination of those things have to have a correct sign in order to push the mass to charge ratio for black holes down. Now let's work in 4 dimensions. And we can ask exactly this way. We can work in any number of dimensions. As Hiroshi alluded to, people have looked at all kinds of compactifications, situations where we know those operators in string theory. You check whether they push you in the right direction. And the answer is that they push you in the right direction. But whatever the higher dimension operators are that we get in string theory, if they're suppressed by the string scale even, there is the running of those operators in the low energy theory. The running of exactly these F to the fourth, F squared R, and R squared operators in the low energy theory. And those running will be proportional to G Newton. So if the string scale is less than the Planck scale, which it is whenever we have weak coupling, it's small, but they're logarithmically growing. So if you wait long enough, if you let the log get big enough, eventually the running pieces will dominate over any pieces that are sitting there suppressed by the string scale already. So that means that there's a question you can ask about super asymptotically large extremal black holes, where the F to the fourth, F squared R, and R squared terms are entirely dominated by the running in the low energy theory, just from graviton loops, any other light particles you have in the low energy theory. And so you can ask whether that pushes you in the correct direction or not. Now that's a computation that you can just flat out do. It's very simple in 4 dimensions. R squared doesn't matter in 4 dimensions. It turns out for very nice reasons that F squared R doesn't run at one loop. So the entire thing boils down to calculating the beta function for the F to the fourth term. Now, I told you in the very beginning that F to the fourth needs to be positive from superluminality constraints. So you really would expect that the coefficient of F to the fourth is guaranteed to come out to be positive. And it is. But then you have the little puzzle that Hiroshi alluded to in his talk, which is why it can be that in supersymmetric theories, this thing is always saturated, and it's 0. This turns out to have a beautiful answer. That you can compute the beta function for the F to the fourth operator in complete generality, and you find that every particle species in the world makes a positive contribution to it, but one. Massless particles of spin 3/2. Okay? So this is a counterpart for the fact that only non-abelian gauge fields can give you minus signs for the running of gauge couplings. And therefore you discover something interesting. In the space of all possible theories, the beta function for F to the fourth is positive, but it can become 0 on the boundary of all possible theories for supergravity theories. Okay? So supersymmetric theories are discovered as the boundary in the space of all possible theories saturating of positivity. Exactly like what we see in the weak gravity conjecture, right? And in fact, this gives an asymptotic proof of the weak gravity conjecture because it tells you that for large enough black holes, the mass to charge ratio is guaranteed to go down, okay? Just from quantum effects, calculable quantum gravity effects in the low energy theory. So my feeling about this is that there's a larger statement about the mass to charge ratio that sort of asymptotes to 1. That we can have calculable quantum effects that push it down, and then there's something different that keeps pushing it down as we go to lower and lower charges. Okay? But this is another example of how these basic things about unitarity, analyticity, and so on are not disconnected from the other questions about about gravity. All right, thank you very much. Thanks.